So I should mention, I worked on a lot of kidney exchange, which is another type of matching market, but I'll talk today about a matching market that maybe some of you have known. The matching markets we're going to look at is markets when agents have heterogeneous preferences. And we're going to look at two-sided markets. So there's agents on both sides. So think about firms and workers, or men and women, so forth. And there's no transfers involved in these markets. Okay, so there's lots of work also with transfers, of course, but here we're not going to consider any transfers. So this nice model was presented by, introduced by Gale and Shapley in a seminal paper in 1962. And matching, a solution concept, an economic solution concept of matching markets is a well-known one is stable matching that has been proven to be very successful in market designs, in centralized market designs, such as the National Residency Matching Program, and in other such labor markets all over the world. And actually see markets that haven't been using this solution concept to try to find stable outcomes, centralized markets have collapsed. There's evidence that Al Roth documented that collapsed over time, and but the successful ones were the ones that used this concept. Also, empirical studies noticed used to analyze decentralized matching markets, such as marriage markets in India and after World War II, and using the solution concept of stable matching. So what is a stable matching? First of all, think in your mind as matching markets, I'm thinking of each agent on each side of the market has preferences of who they want to match to on the other side of the market. Okay? So think about maybe an ordinal list of who's your top choice, second top choice, and so forth. Okay? We'll say a matching is a matching between men and women. So let's think about men on one side, women on the other side. The matching between men and women, one-to-one matching, is stable if you are matched to your third choice. It means that your first or second choice are matched to someone they like better than you. If that's satisfied, then the matching is stable. Otherwise, you can approach this woman, and she will be happy to match to you, and that's not stable. Okay? So that's a stable matching. To find one, Gale and Shapley proposed this very nice algorithm. It's called the deferred acceptance algorithm that you can think about men go to their top choice. Every man goes and proposes to the top choice, I want to be with you. And every woman who gets at least one proposal keeps only her top choice and rejects everybody else. But she keeps it only temporarily. And every rejected man goes to his second top choice and proposes. And now women who have more than one choice, maybe the one that was kept temporarily and maybe a new choices, also, again, keeps only her top preferred choice and rejects everybody else. So every rejected man keeps on proposing down his list until he gets accepted or doesn't match to anyone. And women always keep their best offer so far until this algorithm ends. Once it ends, no man makes any more offers, then we get a stable matching. Okay, so no man can get someone better than he's matched to because he went down his list. Okay, so this algorithm, when men propose, gives you a nice stable matching. It turns out the set of stable matchings is a lattice, and there's one that is best for the men, and one is best for the women. And the best for the men is the worst for the women, and vice versa. Okay, so the men proposing deferred acceptance algorithm gives you the men optimal stable matching, and at the same time the women worst stable matching. Okay. So there's been a lot of literature in economics to study, okay, in centralized markets, who should propose to who, and then maybe things like manipulation in matching markets. Maybe I should change my preferences to, if you run a men proposing deferred acceptance algorithm, maybe women will want to change their preferences to impose a different kind of stable matching and so forth. Okay. What we're going to study in this here is matching markets when preferences are random, heterogeneous and random. Okay, and there's going to be n men in our model, n plus k women. K is any number, non-negative number for now. And we're going to assume that every man has complete preferences over women. So they rank everyone. And the way they rank it is by they draw uniformly at random who is the best choice, second choice, and so forth. So random permutation over the preferred woman. Okay? And the same, every woman, that's how they draw preferences. They draw preferences IID over men. Okay, so this is the model. And the thing we're going to ask is how competition affects the markets in two ways. In competition, I mean, the way we're going to introduce competition is make this k at least 1. So we're going to have more women than men and ask how the market behaves. And I'll show you also some previous results on what happens when the market is balanced. So the questions specifically we're going to answer is how well do men or how do well women do on average in unbalanced matching markets. So we're going to look at the average rank. So this, if mu is a matching, and we can count, if you're matched to your first choice, that's 1. If you're matched to your second choice, that's 2. And now I can count what's the average rank of men in a given stable matching. So I count only over men that are matched. Okay? Or over if the average ranking of women is only over women that are matched. Okay, so we're going to ask, what is the average rank of men? How good is it to be on the short side of the market? And we're going to also ask how likely does that you're going to have more than one stable matching. We're going to ask how many agents have multiple stable outcomes. Okay, so this is the lattice structure. Is this a big? Is there going to be many stable matchings or not? And this is how we're going to answer it. How many people might have different equilibrium outcomes, stable outcomes? Okay, and this is an important question because again it goes back to this: if there's multiple stable outcomes, people might start thinking about how to behave in these markets in order to get better outcomes. It's also important in order for design questions. If you run the National Residency Matching Program, do you want doctors to propose or residency programs to propose? Because that can lead to very different stable outcomes. One that is much better for the doctors, one is much better for the programs, and so forth. Okay. So those are the questions we're going to ask. Yes. Okay.
And
fantastic.
Answers.
Yes.
Can come,
Oh, I didn't turn this.
Now is a natural time for.
This is excellent. Food is always.
Okay. Finding out the answers to these questions from you.
Yes. So if you get a different match in your men optimal or your woman optimal, that's already one agent that has multiple stable outcomes. It could have also many. Okay. So here's some previous results by Boris Peter, Don Knuth, and Motwani, and Peter wrote actually several nice papers about this. And they looked at the same questions, but in a balanced market. There's n men and n women. And they showed first that with high probability, the average ranks in the men optimal stable matching for men is log n, and for women is n by log n. So men are doing much, much better than women in the men optimal stable matching. Okay. This is and the fraction of agents that have multiple stable partners goes to 1 as the market grows. large. Okay, so almost everyone has multiple. The men optimal and the woman optimal will give them different things. Okay, so this is what happens when the market is balanced. Here's some more. So this is these results here that I just mentioned. When I say the core is large, I mean the core is the set of stable matchings in this problem. So Roth and Pearson looked at data from the National Residency Matching Program when they were redesigning this labor market, and they showed that actually the core is small. There's not too many stable outcomes. Most people get the same stable match, and they suggested as a reason is that so that the residents, doctors are only listing a few number of positions, and that creates a lot of competition in the market, and therefore the core is small. Yes?
So in this model, a small core is actually more stable because people have less incentive to deviate like to other stable matches?
So you're putting stable on the stability, but yes, in some sense, yes.
If you want small core,
so there's a result if there's a one-to-one matching market, you can show a result that if there's a single stable outcome, no one can manipulate the preferences to get a better position, get a match. Okay. Yes, so it's more stable in that sense. It's yeah. Okay, so and they suggested those short lists. The short list comes from if labor markets are, if residency programs are interviewing over November, they only have so much time to interview, and that's why that's the people who interview you. Those are the residence programs that interview you. Those are the ones that you're going to run. But if you're going to maybe get much better, you might want to much better options. You might want to interview over a longer time. So why are short lists are happening is an interesting question by itself. There's some results that, so this is what they suggested, and Nicole Imorlica and Mohammad Madian, and then Kojima and Patak showed that, modeled this, and when they showed actually when the lists are short on one side, then the market grows large. Short, and they modeled short as constant length list. When the market grows, but the lists don't, then almost everyone has a unique stable partner. That's what they looked at. And of course, you cannot ask the questions of who gets what in terms of rank because the lists are short from the first place. Holtzman and Salmon show that if preferences are becoming more and more correlated, the core becomes smaller. And that's natural. If everybody agrees who's the top program, that top program will choose who they want to match to. Okay, and so forth. So that's very natural. There's some empirical evidence that documented in different kinds of markets that the core is small some of them after estimating preferences. Some of them took just given preferences from centralized markets, the reported preferences. And the way they checked it after having those preferences, they had to run Gale-Shapley with the men optimal and then the women optimal and see how different they are. Okay, so there's no actually, first of all, we don't know how, the first question that I'm asking here, how well are the men doing and how well are the women doing in unbalanced matching markets? We don't know to answer this except this result, except by running Gale-Shapley. There's no link for market characteristics to outcomes. Okay, they had to go and run these algorithms. There's some sensitivity analysis that shows that if you add a man to the market, then men are worse off in the men optimal stable matching, or are worse off in the women optimal stable matching in a given one. Okay. So here's this previous result by Pitel, Knuth, Motwani, and Pitel. And one typical question you can ask is, what happens if you add one more man to the market? How well are men? And you're running now the men optimal stable matching. So men are still proposing, but now they're on the long side. How well are they going to do? Okay. So what we show is that when there are unequal number of men and women, the short side is much better off in all stable matching. Doesn't matter if it's the men optimal or the women optimal. So it's much more important to be on the short side than to be on the proposing side. Okay. Okay, so there's a sharp effect of competition despite this heterogeneity, and also doesn't matter that the list, everybody ranks everyone. And the core is small. There's very little difference between the men optimal stable matching and the woman optimal stable matching. I will write this more formally in a few slides. So in the sense that almost everyone is going to have a unique stable partner. Okay, so, and this happens if in almost any market, small or large, and if you add just even one more person. Yes?
That was going to be my question. So it doesn't matter on really the magnitude of the inequality?
So the
Magnitude of the
okay, so of the imbalance.
Yeah.
So the magnitude makes it better and better for the shorter side, but it already with one person, it makes tremendous.
The claim is that even if the long side of the scientist making the proposal, it still has the effect of the short side student.
Exactly. Yes. So small core, despite long lists, and uncorrelated preferences. So again, when lists are correlated, it's more easier. Think about this. We're using uniform at random preferences. We don't have a formal result of this, but it's morally kind of, it's the harder case to have a small core. The more correlated it is, the more likely you have a smaller core, the less stable matchings. And a follow-up question, are there really matching markets that have large cores? So all this literature about studying the set of stable matching, is this real or not? And I think that I believe now the answer is no, but I'll try to convince you. So here's a simulation for a market with 40 women. What you see here is the number of men. So for each fixed the number of men, we draw preferences for men and for women, for the 40 women and for the, let's say, 38 number of men. And we see what's the average rank, how you're matched to for men. Okay? And this is, the blue is the men optimal stable matching, and this is the women optimal stable matching. And you see when the market is balanced, men are doing very well in the men optimal stable matching, but very relatively bad in the women optimal stable matching. But this, right when you move to 39 or 41, the difference between those two in terms of rank is almost the same. Yes?
Based on the men's subjective rankings of what they value in life,
So
what
the
looks versus being able to cook.
so the
Wanting children. What do you know?
no, so this is a very abstract model in the sense that I randomly rank who is my first choice, second choice, and third. So markets do have correlation, but think about this as the same tier of kind of people who are very heterogeneous.
So the core is the size of the lattice?
The core is the set of stable matchings, and the smaller it is, the less stable matchings you have. Yeah.
Is it a coincidence that if you switch who proposes but then increment by one, that you get roughly the same value?
So think about this is the women propose, women optimal stable matching. So it's going to be just symmetric.
Right, but if the men propose, I'm basically saying the red curve is, I think that's right.
The red curve is the women propose, and this is the average rank of men.
So if you shift it to the right, then you get roughly the blue curve. I'm wondering if that's a coincidence.
What is shift to the right? I'm not sure.
Take the red curve and
Yeah.
move it to the right.
Okay.
It looks like you land right on the blue.
Oh, so that's an interesting question. If it's exactly, there's a result in auction theory that says if you design the optimal auction, you can design the optimal auction, but if you get another bidder, actually, you don't need to do the optimal auction. And I wonder if there's something similar here.
Unequal is right, but it's not the value, it's not the 40.
Yeah, but also here, I don't think you get exactly the same curve, but never mind. That's a different. I don't know. What is this line? This is we call it RSD. It's the random serial dictatorship. Ignore for a second the the preferences of women and just draw randomly an order of men and let them choose one by one. So the first man will choose who he likes the most, and every subsequent man will choose his most preferred woman that is still not chosen. Okay? And this is the average rank you get. So when there's less men than women, the average rank is the same as if we ignore women's preferences and let just men choose one by one in random order. Okay, so that's another result in the paper. Okay. So here's what happens to the percentage of people or percentage of men that have more than one stable outcome. When the men optimal and women optimal are different, and then when the market is balanced, 40 men and 40 women, this is the percentage, about 60-something. And when you start moving from slightly imbalanced, it drops a lot. Okay, and it drops pretty quickly to 0. Okay, so this imbalance really, even in, I'll show you for large markets, but also you see here for small markets, the course shrinks very quickly. So here's a formal result. I will show you special cases in a few slides, but this is the general result with any k. The average rank of men, or you can plug here, for example, k equals 1 is about log n. And for in any stable matching, they get about log n. And for in any stable matching, women get at least n by log n when there's more women than men. Okay, so that's regardless of which stable matching you choose, men are doing much better off because there are no short side. Okay, and here's inequalities about the difference. The difference between the women optimal stable matching and the men optimal stable matching is very small, in the sense that if you go and do now women proposing deferred acceptance, it doesn't matter so much to men. They're just happy to be on the short side of the market. Okay? And here's the last result, that very few people are getting different stable, have the option of different stable partners. And this basically implies that if you run a centralized matching markets when the solution concept is a stable matching, or you're looking for a stable outcome, there's almost no reason to manipulate your preferences here, because you're not very likely to be one of those few, and you might actually get be unmatched or things like that. So you just might as well just report your true preferences. Yes.
The little o of 1 and little o of n are even for k equals 1?
Yes.
That's asymptotic in n?
Yes. Yeah. Okay, so with high probability under all stable matching, men do almost as well as they would if they ignore women's preferences. That's the green line, and women are either unmatched or roughly getting randomly assigned men. Yeah. So just get one more person to the party. Okay, and the core is small. That's the result. Okay, so here's the case for 1. If you just add one more women, then men get in any stable matching about log n. And for any stable matching, women get at least n by log n. So here's some numbers. If the market is 1,000, then log n is 7. So you guys are computer scientists. You know these numbers very well. So I put those numbers for in economics because for them, log n and n by log n, both of them, if you normalize, go to 0, and then it's the same. But yeah. Okay, so here's what happens if you have a linear fraction of additional women. Then you will get men will get on average a constant rank, and women will get be chosen almost randomly, okay, n over a constant. So. And this is actually not very hard to prove, and it's a corollary from another work I did on matching with couples. But think about this: is that there's a linear extra number of men or women out there, then you will start run the Gale-Chapter, you'll start applying to your first choice, second choice. Very quickly, you'll find a woman that nobody is matched to. Okay, there's just a lot of women. Okay. Any questions? Okay. So let me, so one strategic implication is what I mentioned about misreporting your preferences. One way to get to, if you get a random men proposing deferred acceptance algorithm, women can possibly manipulate by truncating their preferences. So they will say, people below my 10th choice are not acceptable, and by that, they might impose some better outcome for themselves. But this result says that it's very risky, and you might remain unmatched. Because there's only a single, if there's only a single stable outcome there, then you might fail to do this well. You don't have another option. Okay. So there's the strategic implication. Now intuition. So what is going on here? So if you have a market with n buyers and n sellers, but sellers are completely homogeneous and they're selling exactly the same good. Okay, and all they have to do is fix prices. Then the only competitive equilibrium here, or competitive price, or the price that the sellers are going to sell the goods, is going to be 0 if, or maybe before this, if the market is balanced, they can sell the good for any price. But if you add one more seller, the only price that they're going to sell it in equilibrium is going to be 0. Okay, because if it's not 0, someone will cut down the price, and so forth. It will go and will go shrink very quickly to 0. Okay, but in our model, there's both heterogeneous preferences, and there's no money involved. So it's not exactly the same, but so let me explain what is going on here. If you add one extra woman to the market, maybe not all men are happier to go and match to that extra woman, but some will be happy to replace their current match and go to match her. And now some women became free if some men, or at least that woman that those men are matched to are becoming now outside options for other men. So this kind of thing is rippling through the whole market and makes men so much better off. So this extra woman is becoming an outside option for some men. Their women are becoming extra outside option for other men because of the first woman. So it's an indirect kind of outside option chain. Okay, so this is what's going on here. Another intuition is there's a well-known result in matching markets. It's called the rural hospital theorem that says that in all stable matchings, exactly the same people are going to be matched. Okay, so you can prove you can actually show a simple result. Well, it's not so simple given you have to use Pitel here, but you can argue that if it's always exactly the same men that are matched, the same women that are matched, you can't find a woman that will make the men's rank much worse off than log n. Otherwise, some men will deviate and will go on and match her, and that will contradict this rural hospital theorem. Okay, so that's another intuition for what's going on. But this chain of indirect outside option is what happens here and collapses. It makes the market collapse to one outcome. Okay, so how are we going to show this? We're going to propose an algorithm that first uses the men proposing deferred acceptance algorithm. So when I'm going to propose, we're going to count the proposals until we reach this men optimal stable matching. And from there, we're going to move from the men optimal stable matching to the woman optimal stable matching using similar ideas of proposals as in the men proposing deferred acceptance algorithm. And we're still going to count proposals here. And we're going to keep track on who has more than one stable outcome. So I'll describe this exactly. But this is what we're going to do, those two things. So the first one is the men proposing deferred acceptance algorithm. What I described at the beginning, every man is going to propose to his top choice. A woman that gets more than one choice rejects everybody that except her most preferred choice, reject everybody else. A rejected man always goes and proposes to his next woman on his list, and by that he starts kind of a chain. So if I propose to my next preferred woman, she might accept me or might not. If she accepts me, she rejects someone else, and that rejected man goes and proposes to the next woman, and so forth. So rejected men always keep on proposing to the list. Women always keep the best outcomes and keep on going. So this will get you to the men optimal stable matching. Okay? And then from the men optimal stable matching, we will move to the woman optimal stable matching as follows. So suppose a woman is matched to her, in the men optimal stable matching, a woman that is matched to her worst stable match, okay? Because it's a lattice structure. So what we'll do is going to let this woman divorce her current match, and that man that is forced to be divorced is going to propose to his next woman on his list and start a chain, just like as in the deferred acceptance algorithm. So we're going to force a divorce for that woman and see if such a divorce can cause a chain, trigger a chain that will go back to her with someone she likes better. If that chain goes back to her, then she found a better stable outcome. Okay? So I will demonstrate this with some, I have some pictures to show this, but, and so when this woman divorces this man and he triggers a rejection chain, this chain can end in two possible ways. One is this improvement phase if this chain goes back to her, and then she has a better stable match. But the other option is that chain goes to a woman that is unmatched. Let's say there's only n plus 1 woman, and let's call this, so there's one extra woman that is not unmatched. And she's never unmatched because of the rural hospital theorem, no stable matching. So if this chain now that this woman W hat triggers by divorcing her man goes to this extra woman, we know that W hat doesn't have a better stable outcome. Okay? So those are the two possibilities when, essentially she's trying to truncate her list to get a better stable outcome. And if it goes back to her, she's lucky. If not, she doesn't have a better stable outcome. Okay, so that's what we're going to track. Here's the entire algorithm. I won't go exactly over this. I'll show you some animation for this. So let's say we run the men optimal stable matching. Okay? And now we found that in the men optimal stable matching, woman 1 is matched to man 1. I want to see if woman 1 has a better stable outcome. So she is going to divorce man 1. Okay? And man 1 is going to propose to his next preferred woman on his list. So he starts to propose. Maybe he doesn't get accepted by some woman who was already matched to someone she likes better than man 1. Then he goes and proposes to someone else until he finds someone, woman 2 here, that is happy to accept him. She prefers M1 over her current match M2. Okay? Okay, again, all this purpose is to see if W1 has a better stable match. And now man 2 is rejected. And he goes and proposes. And he goes to W3. And if W3 accepts the M2, she rejects M3. And maybe now this whole chain goes back to W1. OK, so W1 prefers, she accepts M3 if she prefers M3 over M1, the man that she rejected. Otherwise, she will reject it. So what we have here is W1 found a better stable outcome. But not only she did found a better stable outcome, also W2 and W3 found a better stable outcome. Okay, each one of them could have started this chain, and it would have been a loop here. Okay, so what we do in this case is, first of all, we remember that now woman 1 is matched to man 3, and we want to see if she has even a better stable man. So she keeps on divorcing. So we want to go from the men optimal stable matching to the woman optimal. So I need to keep on doing this. So now she's going to reject M3, and he's going to propose, and until he finds someone who is a woman that accepts him. So here's W4, and W4 prefers M3 over M4. So she rejects M4. M4 goes and proposes, and so forth. But now another possibility to terminate is when this chain goes to this unmatched woman, the woman that was unmatched already on the men proposing deferred acceptance. And she's unmatched in all stable matches. Okay? So in this case, we know that for W1, M3 is their best stable match. Okay? But we know much more than that. We know also that so first of all, we record this matching, but we know that all of these women, W1, W4, W5, have found their best stable match. Because if W4 would have rejected M4 to see if she has a better stable match, we know exactly where this chain would have gone to. We know the preferences now. Okay, and it would go exactly over here. So all of these women, including W bars that cannot have a stable match, have found their best stable outcome. Okay, and this is an important part of the proof that we do in the paper, is to show how quickly this set of women that already found their best stable match is expanding, and it grows very, very quickly. So now you can, so for those women, we don't need to worry anymore. I want to find for every woman the best stable match. So now I go to woman 8 and want to see if she has a better stable match. So she divorces M8, and now she starts looking. And it could be that if that set is large, that one of their next proposal will go to one of those women. And if one of those women prefer M8, let's say W4 prefers M8 over M4, we know exactly where this chain is going to. Okay, it's going to end in W bar, and that means that also W8 now has found her best stable outcome. Okay, so very, very quickly, this set is going to grow very, very large, and almost all chains will go through this set, and then we know that everybody found their best stable outcome. Okay. Okay, so this is the essence of the proof, and we keep what we do in this algorithm is we keep we start with some we want to go for all women and update if they find for them the best stable match, and we keep track of a set, we call it S, for the set of women that are already been found for them all their best stable partner. And and this is the set we're keeping track of. And once we find a chain that ends in this unmatched woman, or in the set S, we add all the women in this chain that accepted proposal in this chain to this set of women that accepted proposal in this chain. Okay, and that's what we analyze, this set of stable men and women who found their best stable partners, this set S. Okay? So the analysis, I won't go completely over, but the men proposing, so this is the intuition of what happens. So the men, to get what's the average rank of the men proposal deferred acceptance, you can analyze bounded below and above with using a coupons collector problem. Basically, you need to draw n coupons out of n plus k distinct coupons, and that's a lower bound, and you can do a similar upper bound to rank. And this is actually what Pitel did to find that the average rank is log n. And then we move from the men optimal stable matching to the woman optimal stable matching. This is more involved, but maybe I'll give you first the intuition that is wrong, but and then so if a woman now is divorcing her man, then let's look at the first woman, and she's divorcing her man. the time that the chain, if there's only one extra woman, the time that the chain is going to get to this extra woman is roughly is of linear order, okay? Because to each new women at this stage didn't make so many proposals. They made every one of them on average they made log n proposal. So the time it will get to this extra woman is going to be she will accept a proposal with 1 over n probability. So it's going to be a geometric distribution with 1 over n. But also coming back to that woman is about 1 over the probability that every proposal goes back to her is about 1 over n. So that chain already is going to, the first chain is already going to consist of a lot of women. What I'm cheating here is that could be some internal cycles in this chain. And that's something that we have to deal with and remove those internal cycles. So that's more complicated, but you can see already that the first chain is going to be, we can show that it's about square root n. This is using birthday paradox arguments, but it's already going to be a large set of women. Once the first chain goes to this extra woman, you're going to already add square root n women to the set S, and that's already pretty large. From there, you need to still show that it grows quicker. And at some point, once it's linear, or not even linear, almost every proposal will go through that set. So that's what's happening here. OK. So this is the logic. Any questions about this? OK. So altogether, very few women will be part of improvement cycles. Almost all phases will be terminal phases. And therefore, almost all women or all men have a unique stable partner. OK? OK, what about correlation in preferences? So we have uniform. We have here uniform random preferences. And you might think that there's tiers in labor markets also. So here's some examples. So first of all, perfect correlation will lead to a unique core. If everybody agrees who's the top woman, that woman will just choose who she wants to match to. But you can work a little bit more with this model. So first, understanding what is the short side doesn't depend just on n and k. So you need to be more careful. So there could be a market with 15 women, 15 men, 20 women. Top 10 of the women are top women, and 10 medium women. So here, of course, there's first of all this. You can solve this market first with the 15 men and the top women, top 10 women, who are going to do great in that market. But then there's going to be remaining 5 men who are going to be matched to the remaining 10 medium women. OK, so the rank will a bit change. You need to be careful here. But the small core is going to remain, because there's going to be a small core in the first market, and then in the remaining market, there's still going to be a small core. OK, so this is identifying what is short and long is an interesting question. Here's some simulations with correlation. What you see here, this is the men average ranks of wives. Again, the blue is men optimal stable matching, and the red is women optimal stable matching. And what we draw here is there's some epsilon is coming from a Gumbel distribution, or extreme value 1 distribution. So this is representing some idiosyncratic taste. And beta is some correlation parameter. And if beta goes to 0, this is complete uniform at random. If beta goes to 1, or to infinity, then this is everybody agrees who's the best woman, second best woman, and so forth. OK? And this is what you get when you have more and more correlation. First of all, this is the percentage of or maybe before this. So if everybody agrees who's the best woman, the women are choosing, OK? And if it's completely idiosyncratic, the men are choosing, in the sense that the average rank is much better for men. This is the percentage of stable matching. It's not monotone, but it's still not high here. So it doesn't go to the 60%. So it's still an interesting question. Do general markets have small core? And this is the random serial dictatorship. Okay, so even if there's more women than men, if everybody agrees who is the best woman, they are actually choosing, and it's not the men, even if you run men proposing deferred acceptance. Okay. So the ranking result is a bit fragile to correlation, but the core still stays small in the sense that you see it's almost the same. It's almost the same everywhere. And if here, this is just if you zoom to this area, so this is what happens. They look almost the same, at least, with the random serial dictatorship algorithm. Here's some results from other markets we simulated with uniform random preferences. And you see here when the market is completely balanced, the difference between men optimal and women optimal is very big in terms of rank. But if you move here to +1 and -1, men here are doing much better than here, and this is pretty close. And you can check maybe later these numbers if this is moving the graph. So we have this in the paper. I think there is some result hiding there. But so for 5,000, you see the difference is huge, but here it doesn't matter much. So we did some. Here's the percentage of stable matchings. So it quickly goes to 100, and it shrinks very quickly if you're unbalanced. Percentage of people who have multiple stable partners. And also here's for more simulations results for it. This is for a market with 1 million, men optimal, women optimal, and percentages. In parentheses is just standard deviation. OK. So to conclude here, since I have a little bit of time, maybe I'll. So until what time do I have? 1?
We have to be out of the room at 1.
At 1. Oh, OK. So I don't have time. Good. So OK. So exactly. So to conclude, random unbalanced matching markets are very competitive. So how I view the previous results is that, first of all, those short list assumptions are creating a lot of competition because there's a lot of miscoordination. And essentially, if you people, those results that model ranking lists to be constant length, what they essentially do is create a very imbalanced market because lots of people will remain even unranked. And also correlation creates competition because if more people agree who is the best woman, then there's it's like a tiered market. Everybody's competing for that woman, and then for the second, and so forth. I think what we get here is that we model competition in probably the most weakest way by just adding one woman and keeping lists long and getting a small core, and also this result that short side chooses, essentially, in all stable matching. Now, another, I think there's interesting more questions here when think about firms and workers, and the firms are on the short side, they get typically their log n rank. And what if they're on the long side? Is that a reasonable market? Then you want to ask questions about, for example, interviewing. Who should I interview? Who should I target in markets to even approach to and to list for? Those questions are hardly being answered, and I think those are interesting. And I think maybe those large markets models can also be useful in, when we're talking about interviews, also be about learning from other people's interviews, adverse selection and things like that, or what you call privacy. Can I learn about this candidate from what you're doing? And maybe these kind of models can help in analyzing. Usually those small markets are very difficult to analyze, but with large markets, maybe you can get along a better chance. Yeah. Yes.
So this might be a silly question, but in the balanced case, let's say we're not making any assumptions about coordination of purposes and the men are proposing. So you have the men proposing in some order, right? So regardless of whether we switch up that order, it's still going to be stable, the ranking scale shaping. But does the
No. Gale-Shapley, the order doesn't matter at all. The outcome will be the same.
So is that, so is the average rank, affected by the order in which men
No.
propose in the unbalanced case?
No. No. The average ranking will be a little bit different if women propose versus men propose. But given who proposes, it doesn't matter. It doesn't matter balanced or not balanced in any market. Yeah. Yeah.
You were thinking about correlation. Do you only think about that all the men have this correlated preference on women, but and the other side, but did you already consider that the A's preference on B is a correlation of B's preference on A? Did you consider this kind of correlation?
Also here, no, only one side. One side was uniform, one side was correlated. Preferences, yes. That's what we consider that. Yeah.
Maybe the most difficult example when the core is largest is when it's uniform.
When it's uniform. I don't have a proof of this, but
for example, if you do such a correlation that my preference or
is the opposite.
is negatively correlated and her preference is on me, then it can be even larger.
So it could be. Well, it's worth checking. My guess is that you won't find a large core, but maybe in random markets, not constructing by hand, but yeah. But yeah. So you see here, I think one of the main takeaways is also that you can say something about the outcomes here without running Gale-Shapley at all. I don't care about, I can tell you what the market will look like without using these algorithms which were used all the time. Yes?
One of the points is the core being small, or the kinds of results you have about the core being small, have algorithmic implications, that it's one can find the stable matching more quickly?
So I'm not sure about that. I didn't, yeah. It's a good question. I don't know. Yes?
Are there people doing empirical work where they're trying to fit a heterogeneous model of the preference or the participants in the market to the data, maybe trying to look the cluster of different types or this type of thing, and I guess more generally,
empirical?
Data available to other people to play with?
So the first question is, are you asking empirically or theoretically?
Yeah.
Theoretically.
Are people doing empirical studies of heterogeneity or structure of the preferences in actual matching markets?
Yeah.
And is the data available for those?
So I know, so there's the empirical studies I mentioned by Otachu and Ariely about in dating markets. I don't know if that data is available. Maybe that's something to. And there's others. The National Residency Matching Program is impossible to get data. I have a data that from psychology markets, labor market. It's not huge. You can ask to get permission to use this. I know who to approach. And I think they'll be willing to share this data. It's about 3,000 jobs. This is the size of the one. And there's also this work by Duflo and Banerjee about the Indian marriage market. I don't know if that data is available. It's a good question. There's some school choice data. I don't know if available, but I think it's possible to get. I don't know. But that's a little bit. It's a bit different. But maybe in New York, the people to ask is Al and Parag, I think, or Yunkuche, maybe. But yeah, data should be more available.
We can talk about that later.
Yeah. Okay. Exactly.
All right, so let's thank Itai again.
Thank you.